Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for March 27th, 2013.
On today's show, glasses-free 3D goes mobile, the strongest signal yet of the photonic spin Hall effect is obtained by a metamaterial, a new theory suggests an unconventional use for EMCCD, tests reveal the hazards of laser pointers, tailored photons are generated from solid-state chips, and photoacoustic microscopy receives a grant from the National Science Foundation.
A new glasses-free 3D display is particularly well suited for mobile devices. The new approach uses diffractive optics to produce 3D images, both static and moving, that can be viewed from multiple angles. While other technology shows 3D only when you move your head left or right, or horizontal parallax view, the technology developed at Hewlett-Packard Laboratories does 3D for full parallax, which means you can move your head around the display or rotate it in any direction and still see a 3D image. Here's lead researcher Dr. David Fatal explaining some of the other key factors of the technology.
One of the key factors of the technology is that it actually was designed to be very easy to animate at video rate. So we are aiming to achieve moving holograms in some way. Another very important feature of the technology is that it's compact and portable, and we think we can make it at quite low cost. Now, what I call the cherry on the cake, it wasn't intentional initially, but we turned out we can make it almost the same ways that we actually end up having a transparent display technology. So we've built current prototypes that actually are completely transparent, and then we think that even using a modulating device to achieve video rate, we can still retain most of the transparency. Okay. And the last thing is that there are reasons why the display technology that we develop might be very power efficient, more so than current liquid crystal displays, for example, even though we don't demonstrate it in the paper yet.
The HP team says that in the not too distant future, the technology could make its way to smartphones, smartwatches, and tablets. They also believe it has important applications in 3D mapping, medicine, and surgery, among others. The paper appears in Nature.
The strongest signal yet of the photonic spin Hall effect was obtained using a metamaterial surface constructed of V-shaped gold nanoantennas. The spin Hall effect describes the curved path that spinning electrons follow as they move through a semiconductor. The quantum mechanical optical phenomenon could play a prominent role in computing. While the photonic spin Hall effect is known to exist in nature, it's been very hard to detect. Berkeley Lab researchers amplified the naturally weak signal by measuring polarized light incident on a 2D sheet of gold nanoantennas, whose geometry could be configured by adjusting the length and orientation of the arms of the Vs. The metamaterial makes the effect observable even with a simple camera. The team realized that they can not only enhance the effect, but harness it too. The work appears in Science.
Electrical engineers at the University of Texas at Dallas theorized that sharper microscopic images may be in sight with a method that uses standard low-light electron multiplying CCD cameras in a highly unconventional setting to reduce noise and minimize image deterioration. By increasing the magnification of the image to reduce the number of photons detected in each image pixel, they significantly reduced camera noise and reduced the negative effect of pixelation. The particle localization accuracy attained was twice as high as that gathered through conventional EMCCD imaging. The research appears in Nature Methods.
Do you use a laser pointer? Chances are it's illegally powerful. Of the 122 laser pointers tested recently by the National Institute of Standards and Technology, nearly 90% of the green and about 44% of the red were out of compliance with federal safety regulations. NIST found that both types emitted more visible power than allowed under the Code of Federal Regulations, and that green ones often emitted unacceptable infrared levels as well. The tests were done on randomly selected commercial laser devices labeled as Class 3A or 3R and sold as suitable for classroom use. Such lasers are limited to 5 milliwatts maximum emission in the visible and less than 2 milliwatts in the infrared. About half of the tested devices emitted power levels at least twice the limit at 1 or more wavelengths, with the highest measured output more than 10 times the legal limit. NIST has provided their data to the FDA.
A technique to generate high-quality single photons with tailored properties from solid-state devices could bring us a step closer to a quantum internet. Qubits or quantum bits can carry information quickly and reliably across long distances, provided that all photons in the network are identical. The quality of photons generated from solid-state qubits, including quantum dots, can be low because of decoherence mechanisms within the materials. With each emitted photon being unique, developing a quantum photonic network has proven difficult. A team at Cambridge, however, developed a semiconductor Schottky diode device containing individually addressable quantum dots as their photon source. The dots' transitions were used to generate single photons via resonance fluorescence, which avoided photon decoherence and enabled photons identical to those produced by a laser.
To determine a cell's metabolism, you need to know how much oxygen it consumes. But current technology limits this study to groups of cells, not individual ones. But Dr. Lihong Wang of Washington University in St. Louis plans to change all that. Wang has received a 3-year, $300,000 grant from the National Science Foundation to study oxygen consumption rates of individual cells using photoacoustic microscopy, a novel imaging method he developed that uses light and sound to measure change. Wang says he will measure oxygen consumption on a per-cell basis, but measure many cells at the same time, giving a high specificity and a high-speed, high-yield throughput. The result is the ability to rapidly map distributions of cellular metabolism. Potential applications include gauging cellular health and metabolic state for stress response. The technique also could be used in toxicity studies.
For more on Dr. Wang's photoacoustic microscopy technique, our webinar with him is available on demand at photonics.com/webinars.
Well, that's it for this edition of Light Matters, Photonics Media's weekly newscast.
As always, you can write to us with your comments or questions at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week.
We're developing imaging techniques. We want to look at techniques to replace X-rays, and so instead of having ionizing radiation, we're looking in the near infrared. My favorite application would be to use this technique on children because parents are worried about X-rays. They don't want their kids to have too many X-rays. In near infrared transillumination and reflected measurements, they could go to the dental office and have their a dentist image their teeth every time, and there would be no exposure to X-rays.